Hello class, I hope you're having a wonderful day. So what I would like to do for this practice problem is discuss an object that is in free fall. And whenever we describe an object that is in free fall, what we're really saying is the object is only being influenced by the force of gravity. So an object is dropped and it's falling through the air under the influence of gravity. So let's go ahead and get started. So our practice problem today says a stone is dropped from a tall bridge. The stone is in free fall for 2.75 seconds before it hits the water below. So we have two parts to this problem. The first part to this problem asks us to calculate the stone's velocity after a time of 2.75 seconds. And the second half of our problem asks us to calculate the displacement of the stone. So first thing I want to do is draw a simple picture and label some of our information. So let's say that you are on a bridge here and you are going to drop this stone. It's going to fall and hit the water here. So this is you. Here's the stone. You're going to drop the stone and it's going to fall into the water below. So we know that the initial velocity of the stone in the y direction is 0 meters per second. And what we want to do is label the final velocity of the stone. Now I'm going to use the subscript of hit water. So what we're going to do is calculate the velocity of the stone as soon as it hits the water. Now I also want to label my change in displacement. So delta D sub hit water. So this is going to describe the stone's change in displacement from the position that you're holding it in your hand to the final position right here below when it hits the water. And the problem also gives us the time interval that it takes to hit the water. So delta T sub hit water. This is 2.75 seconds. And we also know one more piece of information, and this is the acceleration due to gravity. So whenever you're holding this stone and you drop it, you know that the stone is going to accelerate towards the earth at negative 9.8 meters per second squared. And it's important that we identify this negative here because acceleration is a vector, and remember a vector shows both magnitude and direction. So that negative sign there is indicating a negative y direction. So acceleration due to gravity identified by lowercase g is equal to negative 9.8 meters per second squared. So first half of our problem, calculate the stone's velocity after 2.75 seconds in free fall. What let's do is start with the base equation for acceleration. We know it's the change in velocity, so final velocity minus initial velocity divided by delta t, and this is the time interval. Now, what I want to do is we're going to use this equation, but I want to be a little bit more specific with my variables. So the acceleration of the stone, remember, the stone's in free fall. It's the acceleration due to gravity, identified by lowercase g. The final velocity is the velocity that the stone has when it hits the water. So I'm going to use the subscript of hit water minus my initial velocity. Well, this is the initial velocity in the y direction. We're going to divide this by delta t, so the time interval to hit the water. Now, if we refer to the picture that we drew here, we have already identified the initial velocity in the y direction, and it's at rest. It's 0 meters per second. So what I'm going to do, come over here, this guy goes to 0. All right, so we don't need to mess with it anymore. Now what we want to do is isolate final velocity to hit the water. How I'm going to do that is multiply both sides of the equal sign by delta t sub hit water. And what's going to happen on the right hand side of the equal sign, our time interval to hit the water will cancel. So let me show you here. Delta t hit water. Okay? What you do to one side, you have to do to the other side. Okay? If you notice on the right hand side of the equal sign, delta t sub hit water is going to cancel. And so that leaves me with the final velocity of the stone when it hits the water is equal to the acceleration due to gravity multiplied by the time interval to hit the water. Okay? So, once again, the acceleration due to gravity, identified by lowercase g, is a negative 9.8 meters per second squared. Okay, my time interval, 2.75 seconds. All right, let's get our calculator out. So I have a negative 9.8 times 2.75. So I have negative 26.95. Okay, so this is my numerical value. We need to take a look at our units now. So our units, we have meters per second squared times seconds. And algebraically, we can write this as seconds over 1. So if you notice here, one of our seconds will cancel. And this will leave us with units of meters per second. So the final velocity that the stone has when it hits the water is a negative 26.95 meters per second. And you might ask, well, what about this negative sign? Is that correct? Well, it is, because remember, velocity is a vector, and a vector shows both magnitude and direction. And so the stone is being accelerated in a negative y direction, and the velocity, our vector, is pointing in a negative y direction. So this negative sign is indicating the direction, okay? So there's our final velocity. This second half of our question is asking us to calculate the displacement. And I've identified this in this simple picture here. So the change in displacement for the stone to hit the water right here. What let's do is use the equation d sub f is equal to d sub I plus the product of the stone's initial velocity and time interval plus 1/2 a delta t squared. All right, I'm going to erase some of this here. I'll leave the answer for the velocity up here. Okay, now what I want to do at this point is be a little bit more specific with my variables. So we're going to use this equation, but we want to adapt this base equation to our situation. So I'm going to be more descriptive with our variables. So right here I have final displacement. So this is the displacement to hit the water. Is equal to my initial displacement plus my initial velocity in the y direction multiplied by my time interval to hit the water plus 1/2 times the acceleration due to gravity. And the acceleration due to gravity is identified by lowercase g times delta t to hit the water squared. Okay? Now, the easy thing about this problem here when we're using this equation, our initial displacement is 0. So let's go ahead and cancel this out. 0. The initial velocity in the y direction, we have already identified this. This is 0 meters per second. So 0 times any time interval. Now, it told us in the problem that the time it takes for the stone to hit the water is 2.75 seconds. but 0 times that value is still 0. So this product goes to 0. So really all we are left with is the final displacement to hit the water is equal to 1/2 times the acceleration due to gravity times the time interval squared. So what we have is 1/2 times negative 9.8 meters per second squared times 2.75 seconds squared, and we're going to have to time that. So according to the order of operations, we have to take care of our exponent first. So 1/2 times negative 9.8 meters per second squared times 2.75 squared. Just to do a reality check, we know we're going to be less than 9. So 7.562 seconds squared. So one thing that I do want to remind you here, when we have a numerical and a unit value squared, we have to square both of them. So not only are we squaring our numerical value, we also have to square the unit value, and that's where we get the 7.562 seconds squared, okay? So this value times negative 9.8 divided by 2. So d sub f to hit the water is equal to a negative 37.06. And let's take a look at our units here. So I have acceleration due to gravity, meters per second squared, times seconds squared, and algebraically we can write this over 1, seconds squared over 1, okay? You can see here that our seconds squared are going to cancel, leaving us with units of meters. So my answer is negative 37.06 meters. And remember that displacement is a vector, so we're required to show both magnitude and direction. And what this negative sign is telling us is this object, this stone, displaces in a negative y direction. So it falls down, and according to our coordinate system, we have down as being the negative direction, okay? All right, so I hope this video has helped you with the stone, the free fall problem. So I hope you have a wonderful day, and as always, if you have any questions, please give me a call. You can email me or you can message me on Canvas. I hope you have a wonderful day.